Hello everyone and welcome back to my channel. Today we're going to be talking about continuity. Before we get into that content, don't forget to like, subscribe, and hit that notification bell. So let's dive in. We're going to be talking about the definition of continuity to start out with. Uh, Things that you need to know. When we talk about continuity, there's overall continuity and continuity at a singular point. So this first part is going to be talking about continuity at a point, and in a little bit we're going to talk about continuity overall. So for you guys, when we talk about continuity, a lot of the times it revolves around can you draw a graph without lifting up your pencil? So we get one step a little bit farther when we get into calculus because it involves limits. So first thing that we need to make sure is that we have a defined y value. So this means we are looking for things like a solid point or a line that goes through it. If we can plug in an x value and get a y value out, that is what a defined point is. The limit as x approaches c of f of x exists, that our line is going towards a singular point. If we have a piecewise function, and we will look at that in a little bit, we need to look at both the left and the right limit and make sure that they are equal in order to do that. The last thing that we need overall is that our solid point and our line are going towards the same spot, so our limit as x approaches c of f of x is equal to f of c. So if we can find the first two, that last one is just making sure they're equal to each other. So let's look at what some of these graphs could look like if they are holding these conditions. So condition 1 is true, but condition 2 is not. So this means that we have a y value at some point. I'm going to use 2. We have a solid point for sure, but our limit does not exist. So that could mean I have a hole up here somewhere, and our graph looks maybe something like this. There are a lot of other options here, but this generally happens when we have that break in our line. Condition 2 is true, but condition 1 does not hold. So condition true means they have a limit. Condition 1 not holding, meaning they don't have a y value. Could be something that looks like this. We'll do it at 2 again. We have a value our lines are going towards, but there is not a specific y value at x equals 2. So our point is not defined, but our limit exists. Conditions 1 and 2 are true, but condition 3 does not hold. So we have a limit that exists, we have a value that exists, but they are not equal to each other. So it could be exactly like that graph I just showed you guys here. But somewhere else we have that solid point. So our limit is going to this y value, whatever it may be, but our actual y value is this one down here because that is our solid point. So we're going to be determining if the function f of x is continuous at 1. So what we're going to do is we are going to go through these 3 things to make sure. So we're going to start with, do we have a y value at that x value? So this first part, we are just going to find f of 1. So we have 3 times 1 squared minus 5 times 1 plus 4. So we have 1 squared, which is 1, times 3. So 3. 5 times 1 plus 4. 3 plus 4 is 7. 7 minus 5 is 2. So we get 2 as our y value. So now what we need to know is that if our limit doesn't equal 2, then I know for a fact that it is not going to be continuous. Or if we get a limit that does not exist, we know for a fact it's not continuous. So now we're going to look at the limit as x approaches 2, as x approaches 1 of our function f of x. Well, our function happens to be a polynomial. It's a quadratic function, so we know that it is a continuous function. There's no division in this problem, so there's no way that we can have some sort of 0 over 0, that indeterminate form. So I know I'm just going to plug it back in. So I have 3 times our x value squared minus 5 times our x value plus 4. It's still 1 because we're looking at the limit as x approaches 1. Well, we just simplified all of this and we got 2. So our limit as x approaches 1 of f of x is 2. So we have our 2 pieces here that we absolutely need. We have our y value that we have now defined as a number, our limit that we have now defined as a number. We now need to make the very pointed statement to say that our limit and our y value are equal to each other. So f of 1 equals the limit as x approaches 1 of f of x. You may be thinking, isn't that redundant? We are already showing that by writing the other 2 statements above. The other 2 statements above are kind of like random facts that we have now written down. The statement we just wrote is the statement to say these random facts are related to each other. So now that we have said that our y value is equal to our limit, we can say, so f of x is continuous at x equals 1. Okay, in my next video, we're going to talk about that back page. It's dealing with some piecewise functions, which might take a little bit more time to kind of talk through.